Remember that differentiation and integration are inverse operations. So if you're taking the derivative with respect to x of an integral with respect to x, you are left with simply the integrand. The following examples serve as an informal guide toward discovering the second fundamental theorem of calculus. Begin by integrating. That would be evaluated from 0 to x. Our result is x squared minus 3x. And that just looks like the integral of this function with x's in our result rather than t's. Notice for part B, we have the derivative of an integral. Well, I already know that this integral is equal to x squared minus 3x from part A. And then we would derive that. And we end up with our integrand in terms of x rather than in terms of t. Do you notice anything yet? It appears that deriving an integral from 0 to x simply gives us the integrand in terms of x. Let's continue. If you're integrating a derivative from 10 to x, then the antiderivative of f prime of t is f of t. And we're evaluating f of t from 10 to x. The result of this definite integral is f of x minus f of 10. Without knowing f of x or f of t, that's as far as we can go. Now, if we were to derive the integral from 10 to x of f prime of t, we just need to take the derivative of our result from part C. When deriving f with respect to x, the derivative is f prime of x. But to derive f of 10, that's just going to be a number, and the derivative of a number or a constant is 0. So how about now? What do you notice? If we're integrating with respect to t from 10 to x, it's simply replacing our t's with x's. So for any constant a, the derivative of the integral from a some number to x of f of t with respect to t will simply be equal to f of x if f is continuous from a to x. The second fundamental theorem of calculus establishes a relationship between a function and its antiderivative. Specifically, for a function f that is continuous over an interval containing the x value of a, the theorem allows us to create a new function by integrating f from a to x. Number 2, part A. This is not technically second fundamental theorem of calculus because there's no deriving involved, but it can help to compare the answers for A and B. The integral of f prime of t with respect to t is simply f of t, and that result should be evaluated from 0 to x squared. F of x squared minus f of 0. Now let's look at part B. This result is f of x squared minus f of 0. We need to derive this result and recall that f of 0 is a constant. Deriving a constant is equal to 0, so we're really just deriving f of x squared. We're deriving with respect to x, but this is not a function of x, it's a function of x squared. Deriving f of x squared requires the chain rule because you're deriving f of some function of x, not just f of x. F prime of x squared times the derivative of that inner function times u prime. We know the derivative of x squared is 2x. So our result is f prime of x squared times 2x. And I think this pesky little u prime or chain rule is the part that trips people up when it comes to second fundamental theorem of calculus. The first one is the simpler one, and then we do the second fundamental theorem on the second. To integrate f prime of t, no chain rule here because no derivative. Now we're going to derive the result from this integral. Each of these inputs, because they are not 1x, will require the chain rule. F prime of the inner function times the derivative of the inner function. F prime of the inner function times the derivative of that inner function. What changes do you notice? The second fundamental theorem of calculus involves deriving an integral. So, if you're ever deriving a function of something other than just x, you have to use the chain rule. If your limits are functions of x, then you must remember to multiply by u prime. And the pattern looks like this. F of v times v prime, f of u times u prime. Time to use the second fundamental theorem of calculus. This time, do not integrate. Use the formula. The first thing I notice is that in the second fundamental theorem of calculus, the lower limit is 0 and the upper limit is x. So they've switched the limits. What does that do to our integral? Important piece of information for a definite integral when the limits are out of order. When a is less than b, and it's the lower limit, and b is the upper limit, nice and easy, fundamental theorem of calculus. But if a is less than b still, but b is the lower limit, and a is the upper limit, because the lower limit has to be less than the upper limit, we rewrite it, but that rewrite has mathematically changed our result to be negative, the result of the original, which means that when you integrate, this would be negative f of b minus f of a quantity. Now, back to the example. We can switch our upper and lower limits as long as we make our entire integrand negative. You can always take that -1 outside of your derivative. The derivative of the integral from 0 to x with respect to t is just the integrand with x instead of t. You can distribute or leave it as is. For part B, notice that this is a definite integral with numbers as its lower and upper limits. That will give you a number answer, a constant. So if you were to derive that constant, whatever it is, your result should be 0. For part C, because our upper limit is a function of x, we will need to use the chain rule version of the second fundamental theorem of calculus. We're not allowed to integrate. They want us to practice using the formula. If u is -1 and v is x cubed, our result should be f of v. That means taking our integrand and plugging in v. So x cubed to the power of 2 plus 2 times x cubed. Also multiply that by the derivative of v, which is 3x squared, minus f of u. When you plug in -1 times the derivative of -1, this simplifies to be 3x squared times x to the 6 plus 2x cubed, or distributed. Now part D is similar to part C, except we don't have a constant for either of our limits. Our lower limit is 2x, our upper limit is 3x. The formula should be f of v prime. Plug in 3x, multiply by the derivative of 3x, plug in u, which is 2x, and multiply by the derivative of 2x. Simplify. Here is our result. Part E, u is f of x, v is g of x, and you know the derivatives of those. Plug in g of x, multiply by g prime. Plug in f of x, multiply by f prime. There's no more simplification I could do. I could distribute, but that won't help me simplify in this case. If f of x is this, then f prime of x is what? So f of x is equal to this integral. They want f prime, so I would derive both sides of the equation in terms of x. That would mean the left side is f prime of x, and the result from the right side will be our answer. The lower limit is a constant. The upper limit is a function of x. F of v is our integrand with 3x squared replacing all t's, multiplied by v prime. Our second piece is multiplied by u prime. Simplified, I get 6x times 1 minus 9x to the fourth, all to the power of 10.